Hello, and welcome to Zeta Potential Analysis, when and how it is useful. This is training module 4 of 6 that were prepared as part of Water Research Foundation Project 5110, Filtration Process Control for Pathogen Removal and Climate Change Adaptation. So to begin our discussion about Zeta Potential Analysis and when and how it is useful, let's first recall that most particles in water are negatively charged. So here we've got our negatively charged particle. This was also discussed in the coagulation basics module, which is module 2 of this series. So as we might imagine, negatively charged particles attract ions and macromolecules of opposite positive charge, typically a compact layer of immobile ions that are strongly adsorbed to the surface forms. And so there we've got our positive charge ions absorbing onto the surface of our negatively charged particle. So this layer subsequently attracts a second layer of ions of opposite polarity. And that second layer is not as tightly held as the inner layer. And there that layer is. And so only part of this broader layer is going to move with the particle in the water. So we've got that inner layer that's absorbed, and then we have part of this outer layer that is going to move with the particle as it moves through the water. So we describe this system as an electrical double layer because there's two distinct layers that surround the charged particle. And they form because of the particle's surface charge and the surrounding counter ions that form this ionic cloud around the particle. So this compact layer of immobile ions that moves with the particle and is strongly absorbed to the particle surface is called the stern layer. The region beyond it is called the diffuse layer, and it should be noted that this region of the diffuse layer extends beyond that dotted line that we talked about, which is the region of particles that moves with the particle as it moves through the system. So that dotted line is called the slip plane or the shear plane or the plane of shear, and it denotes the region of ions and macromolecules that are sometimes also referred to as particles, which makes it more confusing. But here we'll talk about them as ions and macromolecules that move with that negatively charged particle in the water. And again, that slip plane is within that diffuse layer. And that diffuse layer has ions and macromolecules of both positive and negative charge, but as you get closer to the surface of the negatively charged particles, there's more positively charged ions and macromolecules. And so throughout the diffuse layer, that gradient where we have more of the positive charges is getting progressively lower until ultimately we get to the bulk fluid where we have equal concentrations of positive and negative charges within the system. And so because particles have surface charge, an electric potential exists around them. Electric potential is equivalent to voltage. It reflects the energy needed to move against an electric field. So it makes sense that it would be useful for gauging the energy needed to bring two charged surfaces together, like we do in coagulation when we aggregate particles, or in rapid sand filtration when we coagulate smaller colloidal particles and pathogens so that they can approach filter media grains and deposit on them, so that they're ultimately removed from water. And that's something we'll talk about more in module 5. So as seen here in this bottom right side of this image, potential will change as we move away from the particle surface. So here we have electrical potential as a function of distance from particle surface, and we can see that it's decreasing. So the electrical potential within the electric double layer has a maximum value on the particle surface and is very aptly referred to, and not very creatively, but it's called surface potential, so nice and clear. And as I mentioned, the potential drops as we move away from the surface of the particle and ultimately reaches zero at the boundary of the electric double layer. The electric potential on the external boundary of the stern layer, again, very appropriately called the stern potential, and the potential at the slip plane, which is still within the diffuse layer, is called the zeta potential, and it's denoted by the Greek letter zeta. So the zeta potential is attributed to the particle, specifically its surface characteristics, and then also the water matrix and what comprises it. So zeta potential reflects both the initial surface charge of the particle and then whatever is in that accumulated layer around the particle. So it's important to note that zeta potential is a well-known and established concept in analysis. It has been used widely in industries such as consumer products and pharmaceuticals, often to keep emulsions or other suspensions stable. Paints come to mind in keeping them stable so they don't aggregate. And of course, in water treatment, we're looking for the complete opposite. We're looking for aggregation and deposition. And therefore, zeta potential can be a useful tool in some cases because it indicates the magnitude of the electrostatic or charge repulsion and attraction between another particle, this particle and another particle, or this particle and another surface. And so zeta potential is a measure of that magnitude of electrostatic or charge repulsion and attraction between those surfaces. So zeta potential is the potential at the edge of the liquid envelope moving with the particle. And you can see that here in this image. And it speaks to how likely charged particles are to move towards each other or other charged surfaces in the presence of an electric field. And that's why it's sometimes also known as the electrokinetic potential, with electro indicating the electric field and kinetic referring to movement. So I've included this figure on the right. I know it's busy, but it emphasizes that zeta potential values reflect measurements made by electrophoresis, as is indicated here, and that those measurements are used to approximate potential at the shear plane. So we've got that approximation there at the plane of shear, and this potential is the zeta potential, as we see here. This figure also emphasizes that the shear plane is within the diffuse layer or the ion cloud around the particle, as we discussed previously. It's really quite clear in this image. So factors that affect charge will also affect zeta potential. They include things like pH, temperature, ionic strength or conductivity, additives, type and concentration. So we think of coagulants as additives, among other things. So as briefly mentioned earlier, zeta potential has units of voltage, and typically we report it in millivolts. And particles in natural water tend to be between -20 and -40 millivolts in zeta potential. Doesn't mean they can't be outside of it. It's going to vary, as we discussed, as a function of several environmental conditions and the nature of the particle itself. But in general, that's a typical range in natural waters. And one more point to think about when we think about zeta potential, it's one thing to think about zeta potential of a particle, but if we're thinking about particles in water, there are thousands of particles in water. And so like turbidimeters, zeta potential analyzers provide an estimate of the average zeta potential of the particles in water. And of course, that'll be within an acceptable tolerance that's set on the instrument. So one of the things you quickly notice when you use a zeta potential analyzer is that in some cases, the instrument rapidly converges on a zeta potential value. And in other cases, it takes some time because the wide range of particles in the system results in an average that has a wide uncertainty around it or wide variability around it. And therefore, it's harder for the instrument to converge within the specified tolerance. So it's something to be aware of because we can't parse that out, but there is diversity of values. And like with turbidity, you can have 0.5 NTUs of turbidity, and the distribution of particles that results in it can be very different from matrix to matrix. Same thing with zeta potential. So regardless of the method that we use to ensure that it occurs, achieving good particle destabilization during water treatment is essential for well-operated treatment. And zeta potential is the measure that we use to describe particle destabilization. So good particle destabilization here on the left, we have the emphasis for destabilized suspensions aggregating. When particles are destabilized, we get good aggregation, meaning good flocculation and subsequent sedimentation. And on the right, we've got good particle deposition and removal during rapid or chemically assisted filtration. Again, that's discussed more in Module 5, but you see the small particles depositing on the filter media grain surfaces and being removed during filtration. So in situations where the sufficiency of particle destabilization is challenging to assess, Zeta potential analysis can be especially impactful for ensuring well-operated treatment. And that is one of the things we found especially useful in Water Research Foundation Project 5110. And all of that coming together is discussed in the last module, which is module 6 of this series. Before leaving the topic of Zeta potential analysis, however, I wanted to emphasize that it's very important to note that Zeta potential is system specific and will change as a function of the particle type and the matrix in which it's suspended. And so here we have an example of that. This is Zeta potential as a function of pH. The pH dependence of Zeta potential is especially important to discuss because it's important to note that Zeta potential is going to vary with pH, but that doesn't mean that we would change pH in our system in order to be in a range of Zeta potential that's favorable for treatment. So let's talk about this a little bit. So while functional groups on particle surfaces contribute to particle charge, and we discussed that in module 2, their presence is not a prerequisite for charge formation. So even inert surfaces, on them, negative surface charge is formed due to preferential adsorption of hydroxide ions just from water. And inert surfaces thus are negatively charged at neutral and higher or more alkaline pH. It is only at lower pHs where the concentration of hydronium ions in water becomes more dominant. And in those cases, inert surfaces exhibit positive surface charge. So this is the nature of a particle being in water. And so here we've got an example of how Zeta potential can change with pH. The exact shape of this profile is system specific as always, but I have this simplified image to make some key points. So here we see the gray zones with larger absolute values of Zeta potential, and they indicate stable particles in suspension, while the green zones indicate, or the green zone, I guess I should say, indicates unstable or destabilized particles that are more likely to aggregate or deposit on surfaces such as filter media grains. So we're always trying in water treatment to minimize the absolute value, how far we are from zero with Zeta potential. The pH value at which the Zeta potential is 0 millivolts is known as the isoelectric point, or the point of zero charge. Particle destabilization that enables particle aggregation and deposition on surfaces is maximized when Zeta potential is at or near the 0 point of charge. And you can see here I've denoted that maximum destabilization, but you also probably note that that range is smaller than what's denoted as more broadly unstable. And so here's where I think it's important to emphasize that particles can be somewhat unstable naturally. They can flocculate in natural waters without coagulant addition. So a greater extent of destabilization is needed during treatment. And coagulant addition helps to achieve that extent of particle destabilization that is needed to achieve clarifier and filter effluent water quality targets and performance expectations. And so that's in a closer range in and around the 0 point of charge as indicated here with the darker green. Now, of course, particles with Zeta potential outside of these ranges will have more extreme Zeta potentials, and they're generally more stable and less likely to aggregate or deposit on filter surfaces such as filter media grains. But we have to remember when we have particles in a suspension or in just a water matrix, the Zeta potential value we're getting is an average value. And so we have a distribution of particles. And so that one value doesn't exactly indicate any one particular particle depositing or aggregating. So in our project, we've shown that high quality source water requires coagulant addition to the point of maximal or optimal particle destabilization so that we can achieve the 3-log cryptosporidium removal expectations that we have for rapid filtration. And we've seen that we have to be in this tight band around the 0 point of charge. And again, this will be discussed more in module 6 of this series. on this next slide, I just wanted to emphasize the point that was made previously, which is that it is important to note that zeta potential is system specific and will change as a function of the particle type and the matrix in which it's suspended. This is a great example of this. This is an example of a series of natural minerals like pyrite, goethite, and various ferric species under a range of environmental conditions, all and really all very similar particles, but emphasizing how much zeta potential can vary and is thus unique to the combination of particle type and water matrix, or more broadly, the environmental conditions that are surrounding the particle. And you see that it doesn't have to be consistently decreasing. It can decrease and go back up and then down again. It really varies with the system conditions. And so we shouldn't make any assumptions. It's best, of course, like with most things in water treatment, to know your system. So on this slide, we have summarized some of the key takeaways about zeta potential analysis. First, it's critical to remember that zeta potential is system specific and will change as a function of the particle type and the matrix in which the particle is suspended. As well, particles may naturally coagulate in the environment and become destabilized, but that is likely not sufficient for removal of pathogens by filtration. And as discussed, under certain environmental conditions, zeta potential can be very positive or very negative, which leads to stable particle suspensions. And so finally, in the water industry, we use coagulant to help bring zeta potential closer to the isoelectric point, that is a zeta potential of 0, which will maximize aggregation of particles as well as particle deposition on filters. So it should also be mentioned that there are a variety of tools for determining zeta potential. Zeta potential can be determined on macroscopic surfaces, such as membranes or hairs or polymers, as well as from microscopic particles suspended in a liquid. So colloids, nanoparticles, pathogens, other particles in water. In general, there are two types of approaches that are used in the water industry to evaluate zeta potential, and those are electrophoretic methods or electrophoresis, and then streaming potential or streaming current, which are both closely related. So electrophoretic methods separate charged particles under the influence of an electric field according to their size and charge. And so here we have a nice electrophoretic cell where we've got electrodes and a capillary, and as you can see in the image, more negatively charged particles move towards the cathode, and the more positively charged particles move towards the negatively charged anode. And so electrophoretic methods are typically used for particles less than 100 microns in size. And even more typically, they're used for particles, say, less than 10 microns in size. As you can imagine, in these types of measurements and in these types of cells, we're not only measuring zeta potential, there's also gravity present. And so we have to account for that and separate that out. And that's why you don't see electrophoretic methods being used to separate out much, much larger particles or to look at, big membrane surfaces or something like that, because we're actually looking at their movement in water under the presence of an electric field. So the other type of measurement that's commonly used is streaming potential or streaming current. So in streaming potential, the movement of the fluid relative to a solid surface creates an internal electric field due to the transport of charge or the movement of charge within the fluid itself. And therefore, you can evaluate zeta potential. So this works wonderfully. Again, I think membranes are a great example for if we want to have a sense of what the charge is on a membrane, we can create this situation with a very, very narrow constriction, have a fluid moving through, and we can look at the field that's created and estimate zeta potential. So I wanted to say also that it's not that you can't use either of these methods in certain circumstances. It really comes down to having a sense of making sure you're measuring the zeta potential at the point that you need it, and then really looking at is this the right tool for this application? And that's where really knowing your system, piloting, and connecting with the manufacturers of the equipment can be by far the most impactful for this type of analysis. The last point I wanted to make, having done a lot of zeta potential analysis, is it's important to note that when you have low concentrations of particles, what can happen is these analyses can become really challenging in some cases. And this gets at the idea that I previously made about the analyzers taking time to converge on an average value that is within a specific tolerance. And so in these cases, again, if you have a very low concentration of particles in your suspension, this is where you really want to work with the manufacturers and do some piloting to get a sense of the best way to ensure that you're getting the most meaningful data with respect to an assessment of surface charge, and in the case of coagulation and subsequent sedimentation and filtration, really making sure that you have an adequate coagulant dose so that you're sufficiently destabilizing the particles for subsequent treatment. And this again will be discussed with respect to our experiences in Project 5110 with high quality source water and ensuring sufficient removal of cryptosporidium by filtration. And again, that's in Module 6.